There we go, more about magnetism. So our goal in this video is to map the magnetic field, talk a little bit about magnetic forces, see more about the compass, and establish everything we need to know about permanent magnetism. Now the word permanent there is like, not everything in the universe is permanent, but we're talking about devices that generally retain magnetic properties once we've prepared them, whatever that means. We'll talk about that in another video. So I'm going to share my screen again. We're going to look at some stuff and then write some stuff. So here we go. Ba-bum, ba-bum, ba-bum. And right away, all we see here is a typical magnet. And this magnet, this shape of magnet is called a bar magnet, I think for obvious reasons. And how do I know that there's a magnetic field here? We said that a compass detects the magnetic field and that the north pole of the compass points in the direction of the magnetic field at that location in space. And I can just show you that the compass is reacting to being in the space of this magnet. Therefore, I know there's a magnetic field surrounding this iron bar. But there's some basic idea that we want to kind of get to know before we get too far. Right? I have another bar magnet here. You can see the south and the north, the south and the north. Notice here, when I bring north to south, those things attract. North to north, I'm not getting that attraction. In fact, I should be getting repulsion. The reason I'm not is these two objects are so heavy that the static friction between this bar magnet and the ground is canceling out the repulsive force there. But I can, whoop, there we go, turn that around. Maybe I can get this thing to do a little bit of, oh God, no, it doesn't want to do it. Okay, it's too heavy in order to do what I was talking about. Maybe one of these will be helpful, right? I got that, right? Turn that around. Oop, nope, these things are too weak as well. Maybe I'll just do this, right? Oh, this thing is weird. That's what I'm having a problem with, right? It also is a magnet and is affecting it. But what we saw with the bar magnets, and I'm probably confusing this more than helping, is that when I had the north and the south, they attracted. And when I had the north and the north, I should have been getting repulsion. We're just not seeing that. But that's the basic idea. So with magnetic forces, with permanent magnets, two like poles, right? Whether that's north and north or south and south, they are going to repel, and two opposite flavor poles, north and south, those attract. And that should feel pretty good based on what everything we know about electrostatics, okay? Why is that important for us? Well, that's important for us because it really helps us with the compass. So here we go. I'm going to take that away, put my magnet back there, north, south, and now we can see the compass. And if I told you that the compass itself was a magnet, we would see the white end being attracted to this end and this red end being repelled away. So that must mean that the red end of this magnet is the north pole of our compass, and that's the south pole. Just to confirm that, I'm going to bring that all the way over here. Now this end of the compass is attracted to that, so north is attracted to south. Okay, so that's the big idea. This is the north pole of the compass, and it defines the direction of the magnetic field. Meaning, I can put this compass down in a bunch of different locations and say something about what the direction the magnetic field is there. So I'm going to do that. So here, I've got something that looks like that, something that looks like that, something that looks like that. Over here, you can see I've got something that looks like that, something that looks like that, something that looks like that. And so far, you might be saying to yourself, yeah, this feels very much like electrostatics. You know, the electric field near a positive source charge was all arrows radially outwards, and the electric field near a negative was all electric field lines radially inward. Well, things start to get a little freaky when I start going like over here, because now I've got a field that looks like this. And over here, I've got a field that looks like this. And right here, if you notice, I've got a field that looks like this. And if I do the same sort of drawings over here on the bottom, let me move that up so you can see what I'm doing. a different sort of picture arises than just this, what we saw with the electric field with coming out of positive and going into negative. Here, what seems to be happening is our field is looping around from the North Pole to the South Pole, okay? Which feels a little bit different than what was happening with the electric field. So this shape is pretty important here. But the general idea of taking a compass and just mapping out the field, that's super easy. And I could put this in a whole bunch of different ways, but even as you're seeing this, as I'm moving the compass through this space, can you see that it does form that sort of loop shape? And over here, the loop is just, it's different, but the symmetry, right? It seems to be doing that, whereas this one is doing that. So what we want to do is have a better way of visualizing the magnetic field. And thankfully for us, there is. And I just lost a piece of transparency that I was going to use to show this, pushed it off my table. And of course now, because transparencies are clear and it's on the ground, can't see where it went. I'll be back in just half a second. Sorry about that. That was silly. All right. All right, so just put a clear transparency on top of that. So what I also have here are, as you can see, iron filings. And iron filings are just like little shards of iron, little dots of iron. In the same way that when we saw this iron nail was attracted to both the north and south side of this magnet. This is an unmagnetized piece of iron, and it's attracted to all poles of a magnet. These little bits of iron are like little nails, right? And so I'm going to show you what they do when we put them in a space where there is a magnetic field. I'm just going to sprinkle them down. We start to see some structure forming, which is just so cool. Ah, can't overdo it. I think I oversprinkled. There we go. But there you go. And what we start to see are these loops that I was talking about here, right? A loop here, a loop here. You can see the structure of that magnetic field in that space, which is pretty cool. So we can use iron filings as the same thing. What's important to note here is we also have iron filings kind of like on top of the magnet, indicating what's happening in the magnet itself, okay? So it's not apparent from what we just saw. And I'm going to do a little bit of extrapolation. And in a later video, I hopefully will prove to you what I'm saying is true here. But these loops that we were talking about here, and here is the magnet itself, north-south, these loops actually go through the magnetic material, through the magnetic material, through the magnetic material, okay? Through the magnetic material. Boom, and there we go. And we have these closed loops, okay? Because what we're going to see here is that magnetic fields tend to form closed loops, okay? Closed loops, so important. Now, if I were to ask you the question, where is this field the strongest and where is this field the weakest? And thinking about how we drew other field lines. Hopefully what you said is inside the magnet here, where the field lines are densest, we have a stronger magnetic field than out here. And so it's strong near the poles as well. And that's going to be true. So our magnetic field lines were originally not called magnetic field lines. They were called magnetic flux lines. And there's a reason for that. Let's just talk historically. When we originally started talking about the gravitational field and the electric field, they weren't called gravitational field lines and electric field lines. They were called gravitational force lines and electric force lines. But with magnetism, they're not force lines because we showed that the field is not defined by the direction of the force on anything, but by how a compass lines up. So we needed other words for that. And the word here is flux. So magnetic flux lines. The other thing, and this may sound absolutely crazy, but when people were exploring the idea of magnetism and they did this little experiment with their iron filings and they're putting that in the space and they literally looked at the lines themselves. Okay. And they're like, oh, they thought these magnetic flux lines were real things. They thought the iron filings were lining up along real actual things, flux lines that happen in space that were invisible and that the iron revealed them. And the way that they actually initially defined the strength of the magnetic field was by literally counting the number of lines they saw and said, how many lines are there in a certain amount of space? And so that goes back to our other notion about how we have thought about the strength of the field in our pictures, how we have thought about the intensity of the field by looking at the density of the field lines per area informed us something about the strength of the field. And so that is actually how magnetic flux density, which we know today as magnetic field strength, kind of. I say kind of because if you get into higher level physics, there's more specific vocabulary here. I am doing a simplified picture. I know that there's a lot of nuance here that I'm really skipping over. But let's just go with this. So magnetic flux line, magnetic field strength, same thing. But that's so neat that they actually were thinking about those lines per unit area, a flux density. And we give the symbol of capital B for the magnetic flux density or magnetic field lines. I think the reason is because one of the scientists who worked on this in the 1800s was Biot or Biot, B-I-O-T. I'm probably butchering that. And that's the only rationale that I can get for capital B, or we're just running out of letters, right? But that is magnetic flux density. So that's that. And now we have the units of magnetic flux density. I'll just sort of give this to you now. The unit of the magnetic flux density is the Tesla. There are other units for magnetic flux density that are in different scales, but the Tesla is the primary one. Capital T, after Nikolai Tesla, who did a lot of foundational work in our understanding of what's known as electrodynamics, but we'll get there, or sorry, electromagnetism, but we'll get there. All right, cool. So next, what I want to do is look at a couple of other little things. So now what you notice here is I have two magnets in this area. So what's going to happen in this region is I have the magnetic field due to this guy and the magnetic field due to this guy in the same space. What do you think is going to happen here? Well, I don't really have to guess because I can literally just put a compass there and map the field that I see. And when I do that, I map a field that looks like this. Once again, we can see the compass at the space pointing tangent to those lines. There you go. And I can keep doing that. And you can see that that does that. But really, what is that? Well, if I have multiple fields in the same place, hopefully that is just like ringing something in your ears, multiple fields in the same place. How do I find the net field at that location? I use the law of superposition. So what's happening here is that we're doing the superposition of these two fields. Now, you may be asking, well, what happened to the loops you were talking about? Well, that field line continues out through this magnet. That field line is coming through this magnet. And I'll kind of show you something in a minute to substantiate that, but I could do that. If you didn't believe me even from that, we can put down our iron filings and literally just see exactly what I just described. Right? And you could see the filings lining up on those beautiful loops, okay? Or rather on those lines. So there you go. I always look at this picture and I kind of think of mitosis, but no connection there. Just for funsies, let's do another thing there. And instead of doing north and south in that region, I have north and north in that region. Okay, so we're just going to map the field. Notice pointing away, pointing away, pointing away, flip, pointing away, away from that, right? So the field here, it flips around. So some sort of weird thing is going on there with a canceling out of the field, the superposition of those two. And here you go. I can see that there's a field line there. I can see that there's a field line there. That should look really familiar, folks, because if I were to map that out, I would get a field that looks like this, which looks a lot like the field between a positive and a positive charged objects. Once again, these lines are looping back around, which they don't do for the two positive charges. But there's a lot of parallels there, which is sort of neat. I could put the transparency down and show you again, but I do want to kind of keep moving along with this because I'm going to show you something else that is really important. I have to go get another piece of equipment. Unfortunately, I always my basket. Uh, all right. So what I have here is just a little unmagnetized bit of iron, right? But it is iron, so it is a ferromagnetic material. And I'm going to put it in the field there, right? North to south. So let me remind you what we saw when we had this before. We saw a field that looked like that. So now we have this. I'm not going to map it with a compass because what I want to show you is what this field looks like with the iron filings. Okay. Whoa, hold on a second. I think my little iron piece in the middle was magnetized. Let me just check that with my compass. Oh yeah, that thing was strongly magnetized. That is not what I wanted to show you. Ah, good. So this thing is much better. There you go. Let me actually get this up a little. See if I can show you what I need to show you here. Sorry about that. I should have had that prepped, or rather, I did have that prepped in my little basket here, but I think one of my colleagues must have raided the basket between when I put it together. That's what we should be looking at. Yes. Okay. So I had a piece of unmagnetized iron there, and this is the field that we're looking at. So this looks substantially different than what we saw before. We're still getting some flavor of those large things there. But if you notice closer to the iron bar here, it's like some of the field is being redirected into the iron. It almost looks like someone took the field and pinched it. So I'm going to draw what I'm seeing that I hope you saw. And that is a picture that looks like this. Here's my north, here's my south, here's my little bit of iron in the middle. Here's my south, here's my north. And what I saw was this. And then, okay, that there was a little pinching in of the field as it got across. Okay, and then we did see something here. Okay, it's almost like this little bit of iron was like taking the field that was traveling through the air and instead pulled the field into itself because the field could more easily travel through the iron than through the air. And it looks like it's concentrating the magnetic field. That's at least the picture that I want you to go for. And that's because that's what's actually happening. There is something that's known as permeability. Now, I know you've heard the word permeable before. And I'm going to guess the context that you heard the word permeable is in biology, where you talked about the cell wall. And the cell wall was called a semi-permeable membrane, meaning some things could go through it and some things not go through it. And that's what the concept of permeability is. It is a measure of how easily something can go through another thing. In physics, we don't have to say something through another thing. We literally have a more, we were literally talking about magnetism when we use the word permeability. This is a mathematical constant for a material. And by material, I mean like lead, iron, copper, plastic, whatever, the name of the substance, not the object, the substance. The mathematical constant for a material that describes how readily magnetic fields go through them. Okay. So iron, which is a ferromagnetic material, and all the other ferromagnetic materials have a very high permeability. So when something has a high permeability, that means that magnetic fields, and I'll call them B fields, because we just said B is the symbol for magnetic field strength, B fields go through these materials readily. Okay. And in fact, would rather go through these materials than other materials. And so what do I mean there? Well, my iron was surrounded by air. Because iron has a permeability that's like 6 orders of magnitude, like a million times higher than air, the magnetic fields are going to go through the iron rather than through the air. Okay? Let me show you that in one more demonstration. This one I know I have. Where is it? Pardon me. Sorry, there's lots of stuff. I have an iron ring there. Okay, so north and south once again. And I'm going to sprinkle my iron filings. Beautiful. Okay. So the important thing is we can see that sort of pinching into the field. Notice over here and over here, there's not a lot of structure to the filings. And that's because the magnetic field is really weak there or non-existent. But right here, we can see that beautiful structure. But notice here in the center, right? There's no structure. And that is because there is no magnetic field in the center of this ring. The magnetic field is being diverted through the highly permeable iron ring away from the center so that things in the center would not be affected by the magnetic field. And that is a really important idea because that is the idea of what we'll call magnetic shielding, right? So here's the ring. Here's the north-south, south-north. So my field is doing this, right? This. What we're not seeing is the field traveling through this object and avoiding the center, right? So here in here, the magnetic field is 0, and that is magnetic shielding. And I shield something magnetically by surrounding it with a ferromagnetic material. And we shield electronics all the time. If you crack open your phone, don't do it. It voids the warranty and could break the phone. You'll find a thin metal shield around the delicate electronics inside. Same thing of a computer. If you open a desktop up, that's much easier to open up. There's just like a wire frame or wire or metal like that all the components are inside of. That's its magnetic shield. Okay. Most sensitive electrical devices are shielded magnetically by encasing it in ferromagnetic material. Now, here's the great thing. If it's encased in iron, it's encased in a ferromagnetic material, but it's also encased in a metal. And we showed in our electrostatics unit that when you encase something in metal, it's not affected by the electric field of charges outside of it. That's why you're safe in a lightning storm in a car, because the charge will reside on the outside surface of the car, never affect the things inside of it. You're not affected by the lightning. So shielding something magnetically shields it electrically as well. So that's amazing. So by shielding something with a ferromagnetic material, it's inside, it is not affected by external magnetic fields or external electric field. And that notion is called Faraday shielding. Faraday shielding. After Michael Faraday, who is a British scientist who is doing his amazing work in the 1830s, 1840s, 1850s. Okay. And so that's magnetically shielding. The point here is that I can use a compass in order to map the magnetic field because I know north repels from north and south is attracted to north. And I can map the field looking at the notion of the iron filings. And then I see the concept of permeability, which is the degree to which magnetic fields go through something. And that sets us out a good stand for the final question here, which is what's causing all these magnetic fields? I can map them, I can describe them, I can see what's happening with them, but why do they exist in the first place? And that is what our last video will be looking at.